Shall we start now?
Are we? It's already recording. Okay.
Yes, yeah.
Okay.
Do you want to?
Yes, thank you, Jialing Wang from City University of London for coming here to this seminar. We are happy to be with you.
Okay, thanks for the introduction, and thank Heather to invite me to give this talk. So I'm not sure what are the audience interested in, but today I'm going to talk about endotrivial modules for symmetric groups. So my research interest lies in modular representations for group algebra, and so I will mainly work on the category of finite generating module for group algebra. And these endotrivial modules, they play an important part in the modular representations of group algebra. So I want to give a self-contained introduction of these endotrivial modules, and then followed by some known results on the classification of endotrivial modules for different group algebra. And lastly, our results done towards some specific endotrivial modules for symmetric groups. So I will begin. Oh, I should mention that this is a joint work with Karen Erdmann. So I will begin by fix the following notations. So P will be a prime number, and F will be an algebraically closed field of characteristic P. And G is always a finite group with the order divisible by P. So we do want to consider modular representations. And all FG modules are assumed to be finite dimensional, and take two modules n or M tensor product n, I mean tensor over F, and this will again be an FG module. So we will begin on endotrivial modules first. So take an FG module M. The endomorphism ring or endomorphism algebra and M is essentially the home from M to M itself, which is the space of F linear map from M to itself. And the dual of M is the home space from M to F. And in fact, if we consider them as FG modules, we have the fact that the endomorphism ring is isomorphic to the tensor product of M and dual of M. So why is that endotrivial module? We say M is endotrivial if the endomorphism ring decomposes into the trivial module direct sum with some projective FG module as FG module. Or equivalently, the tensor product of M and the dual of M decomposes to F plus projective module P. So this is just the definition for endotrivial. It's quite straightforward. And one of the easiest example would be the trivial module. So take the trivial module F. It will be endotrivial since the dual of F times F is just isomorphic to F. So by definition, is endotrivial. And in fact, all one-dimensional FG module is endotrivial. For example, we know that for the symmetric group, we have a sign module when P is not 2, and that is one-dimensional. And in fact, that is also endotrivial. So given this definition, what else can we say about endotrivial modules? So first of all, in general, we have this surjective module homomorphism from the tensor product of dual of M and M to F. And we sometimes call it evaluation map. So take U times M, it will be sent to U evaluate at M, where U is a linear map from M to F. For this evaluation map, it splits if and only if the dimension of M is not divisible by P. So we know that if M is endotrivial, then the dimension of M cannot be divisible by P. And in fact, M is endotrivial if and only if the kernel of this evaluation map is projective. And I should also point out that in the module category of group algebra, the projective modules and the injective modules, they are the same. Okay. Now, we can say more about the dimension of endotrivial module. So let n be the p part of order of G, then the dimension of M for an endotrivial module M is either plus or minus 1 mod n if P is not 2, or plus minus 1 mod half n if P is 2.
Sorry, what does P part mean?
Okay, so that is the P to the power of A, the largest P to the power of A such that P to the power of A divides the order of G.
Okay, thank you.
Okay, don't worry. Actually, this proposition, you can get it easily because we know that the projective FG module should have order divisible by the P part of order of G. Okay, so what else do we know about these endotrivial modules? So first of all, if we take any endotrivial module M, there will be an indecomposable endotrivial summand M0 such that M is isomorphic to M0 plus projectives, and this summand is unique up to isomorphism. So in a way, we can sort of talk about the minima endotrivial modules, which are the indecomposable ones. And every endotrivial module essentially is just some minima indecomposable ones plus projective. And secondly is that the endotrivial module is closed under taking tensor product, and of course closed under taking dual, because the dual, if you take 2 times dual of M, you will get dual itself, and by definition, dual of M should be endotrivial as well. And also, if M is indecomposable endotrivial, then the vertices of M are P subgroups of G. And last but not least, a module is endotrivial if and only if the restriction to any elementary abelian P subgroup is endotrivial. So it tells you that studying the endotrivial FG module, to study these endotrivial modules for any group G, you should start with studying endotrivial modules for elementary abelian P groups. Okay.
Sorry.
And one thing I want, sorry, yes?
Yeah. What are the vertices of M?
Oh, okay. So that's a good question. So if you have an indecomposable module M, then there exists uniquely up to conjugacy a P group, say Q, such that this Q is minima subject to the condition that there exists FQ module S, which we call the source. And the M will be a summand of S induced from Q to G, and the S will be a summand of M restricted to Q.
Okay.
So so sort of like determining in vertices and sources of indecomposable modules is sort of like a tool to reduce this question of studying indecomposable modules for FG to study indecomposable modules for P groups.
I see.
Okay, and of course, every P subgroup of G should be contained in some P subgroup. So every vertex should be contained in a P subgroup. And this tells us that the vertices of M, if M is indecomposable and endotrivial, should be the largest one, which are the P subgroups.
Right.
Yeah, and we do know that, for example, in the trivial module, they also have vertices as P subgroups. Okay. So one thing I want to point out is that we know here that endotrivial modules, they are closed under taking tensor product, but they are not closed under taking direct sum. So for example, if you take 2 times F, you will not be endotrivial, or you can just directly argue by the dimensions, because just now we say that the dimension should be plus minus 1 modular the p part of order of G. Okay. So moving on, I want to talk about syzygies of modules, but I'm sure you have heard of it. So take any FG module M. Since we are in the module category of group algebra, you have enough projectives. That means every module has a projective cover. And a projective cover is just a minimum projective module P, such that there is a surjection from P to A. And the kernel of this surjection is the first syzygy of M, denoted by omega M. And similarly, you take the injective Hall of M, which is the minima injective module, such that M can be embedded into I. And the co-kernel of this embedding is the negative first syzygy of M. And then you can define any omega n of M inductively. And this omega n of M is called the nth syzygy of M. So the reason I want to see this is because if we have two module Mn and a short exact sequence M to P to N, and the middle term P is projective, then M is endotrivial if and only if N is. And we know that we can when there is a short exact sequence from omega M to P to M. So it tells us that M is endotrivial if and only if omega M is endotrivial. In fact, M is endotrivial if and only if any nth syzygy of M is endotrivial. So this, and recall that previously we already said that the trivial module F is endotrivial. So we immediately get a family of endotrivial modules, which are the syzygies of the trivial module F. And we denote this family of endotrivial module by omega G. And this omega G plays quite an important part as well. Now, last but not least, I want to point out this proposition, which is quite important to understand endotrivial module. So take two more indecomposable modules, one M, which is endotrivial, another N, which is not projective. Then M times N has exactly one non-projective indecomposable summand. Okay. And furthermore, if we let N to be M itself, which means we are considering the second tensor power of M, then it tells us that the second tensor power of M has exactly one non-projective indecomposable summand. And in fact, you can do it inductively. So it tells us any nth symmetric tensor power of M has exactly one non-projective indecomposable summand. And recall that any endotrivial module should have a non-projective endotrivial indecomposable summand. So to sum up, any nth tensor power of M has exactly one non-projective indecomposable summand, and that summand is also endotrivial. And this is regardless of your representation type of this group algebra. So it tells you that even though your FG could have tam or wild representation type, but you have a nice control of things that could appear in the tensor power of endotrivial modules. Now, some motivation of studying these endotrivial modules. So I want to look at the green ring of stable module category of FG. So the green ring of the module category of FG, the elements inside are just modules. The plus is given by direct sum. The multiplication is given by tensor products. So they form a ring. And when I say the green ring of stable module category, it means that we are quotient out those projective modules, because the projective modules, they forms an idea in the green ring. And we want to consider those invertible elements in this green ring. M is invertible if and only if there exists some module n such that m times n is isomorphic to f plus some projective modules.
Sorry, Jay. So
yes?
in order to have a ring, you need to have inverses for addition, right?
Yeah.
You have this in the K-naught, or how you subtract direct summands?
Yes. So you can use you take them as variables and you just take negative ones, because the zero. Yeah.
Okay.
Yeah.
You split Grothendieck group somehow, right? And take.
Well, it's not directly the Grothendieck group, because the Grothendieck group, they sort of the addition are given by short exact sequence, right?
Yeah,
this is more strict. Yeah.
Yeah, you only consider split short exact sequences, right?
Yes,
okay,
exactly.
Yeah, okay. All right.
Yeah.
Cheers.
Okay. So so I want to consider an invertible elements in this green ring, and since endotrivial modules, we know that by definition m times dual of m is f plus projectives. So endotrivial modules are invertible in the green ring. Now, furthermore, by this theorem by Benson and Carlson, so Benson and Carlson showed that take two module m and n, f is a summand of m times n if and only if n is exactly the dual of m and dimension of m is co-primed to p. So what this tells us is that if m is invertible and there exists such n, then this n must be the dual of m, and thus m is endotrivial. So basically what this says is that the set of endotrivial modules are exactly the set of invertible elements in the green ring of a stable module category. And furthermore, since you have m tensor dual of m is isomorphic to f in the stable module category, so tensoring these endotrivial modules gives you stable equivalences on the stable module category of Fg. And in fact, if you take an indecomposable endotrivial module, which does not lies in the same component slender component as K, then tensoring this endotrivial module gives you a graph isomorphism from the Auslander component containing K and the Auslander component containing the module itself. But that's just for your interest. I'm not going to go through more details on these things. What I want to point out is that they are interesting objects in the module category, and that's one of the reasons we want to study them.
And that's every, sorry again. So that's every,
no worry.
So these components have, every component has an endotrivial module associated to them, or not necessarily?
No, not necessarily.
Okay.
Okay. In fact, for some of the cases, the only endotrivial modules you will get is the syzygies of G.
I see.
So you don't get much more things coming out for some of the group algebras.
Right.
Yeah. Okay. So next, I want to talk about the classification has done towards these endotrivial modules for group algebras. So previously, we said that these endotrivial modules, they are closed under taking tensor product and dual, but not direct sum. So I want to define an equivalent relation on the set of endotrivial modules. So we say two endotrivial modules are equivalent if they differed by a projective module. Or to be more explicitly, M is equivalent to N if M plus P is isomorphic to N plus Q for some projective module P and Q. And then you can take the equivalent classes of endotrivial modules. And the group of endotrivial modules of G, denoted by TG, is the set of equivalent classes of and together with the operation plus. So M plus N is the equivalent class containing M tensor with N. So here I use addition is because tensor product is abelian. So M times N is isomorphic to N times M. So you do get a abelian group TG. So that's why I use addition. And the zero element in this group of endotrivial modules is the trivial module because everything times F is self. And the inverse of M is the dual of M because by definition, M times M dual is F. Now, previously we point out that, yes.
Yeah, so this would be somehow the group of units of the green group somehow, or
yes, exactly.
Yeah, okay.
Yes, and this since we mentioned that each endotrivial module they have a unique indecomposable endotrivial summand. So in fact, every class in TG can be represented by an indecomposable endotrivial module. So it tells us that studying TG, we can just studying all the set of all indecomposable endotrivial modules. Okay. So there are several work done towards understanding TG for finite group G. Firstly, this is due to Puig and Kasam, Maza, and Nakano. So they showed that TG is finitely generated. So TG is a finitely generated abelian group. So it can be write as a direct product of the torsion subgroup and the torsion-free subgroup. So the torsion subgroup is just the elements of finite order, and the torsion-free one can be viewed as the quotient of TG, quotient of TT, the torsion subgroup. And I think the TFG, the torsion-free one, is not unique, but the rank of this torsion-free subgroup is unique, is well defined. I should say well defined. Okay. So to study TG, one of the approach is to understand the rank of TFG and what's the torsion subgroup TTG and what are the generators for this torsion-free TFG. Okay. So one important result says that the omega G, which is the syzygy of F, they generate a cyclic direct summand of TG. Okay, but I should point out that over here it didn't say it's a finite summand or infinite one, so it could be both case. So it could be a finitely it could be a finite cyclic group or an infinite cyclic group. And a remark firstly is that in this TFG, if we have n times omega f, is just the nth omega of f. So basically, this is just saying that the indecomposable endotrivial summand of nth syzygy of f is the same as the indecomposable endotrivial summand of nth tensor power of omega of f. So that's why this omega G is a cyclic generator, a cyclic subgroup of TG. And secondly, as I said before, for some of the cases where for example, when G is a finite abelian P group, the group of endotrivial is exactly this cyclic subgroup generated by omega G.
And you know if this is torsion or torsion free, or there are both cases even in that particular example?
Oh yeah, that's a good question. I think there are both cases, if I remember it correctly, but I need to check. Yes. Yes.
Might depend on if P divides G,
Yeah.
or the order of G or something like this.
I think okay, we are always assuming the order of G divides P.
Yeah, of course. Yeah, sorry.
But I think it depends on what kind of P group G is.
Right. Okay.
Yes. So for the torsion-free part, we actually know the rank. So this is done by Apron. So Apron says that let NG denote the number of conjugacy classes of maxima elementary abelian P subgroup of G of order P squared. Then the rank of the torsion-free subgroup is NG if G has P rank no more than 2 and is NG plus 1 otherwise. So the torsion-free part, we do know the rank. So what's left to do is to figure out the torsion part and what are the generators for the torsion-free part. So we know a lot of things already. So when G is abelian P group, we know, and when G is finite group of V type in defining characteristic, and I think I should add more in non-defining characteristic, we also know. And when G has a normal Salo P and or a cyclic Salo P, and when G is symmetric or alternating groups. So we know the classification for these cases and some more. And the case I will be interested in is when G is a symmetric group. So when G, let Sn denote the symmetric group of degree n. So here are the classification given. When P is 2, you don't have the torsion part. And the torsion-free part will be 0 if n no more than 3. And it will be isomorphic to Z squared. So it has a rank 2 when n is 4 or 5. And it will be Z otherwise. So notice that when n is at least 4, you get at least one summand of Z coming in. And this is generated by the syzygy of F. So the syzygy of F always generate a summand Z in this case when n is at least 4. And when n is 4 or 5, you get another copy of Z coming out. So it means that in this case, you have another endotrivial module which doesn't lie in the syzygy of F, and it generates another copy of Z. Now, for the odd P case, you will have slightly complicated description. So when n is less than 2p, you don't get torsion-free part. You only get torsion part. And we do know what this is, but they have a explicit description for this case, but I will omit in here. And when n no more than 3p, at least 2p, you have one copy of Z and 2 copy of C2 coming out. And in the case when n between p squared and p squared plus p, you get 2 copy of Z and 1 copy of C2. And for the rest of the case, you get 1 copy of Z and 1 copy of C2. So in the case when n is at least 2p, you can observe over here, you get at least 1 copy of Z and 1 copy of C2. And that 1 copy of Z comes from the cyclic summand generated by syzygy of F. And that one copy of C2 comes from the sign representation. So the sign representation is a one-dimensional module defined over symmetric group when P is odd. And we do know that the sign tensor with sign is isomorphic to trivial, and it's self-dual. So it will generate a summand or which has order 2. So the interesting case would be, firstly, over here, you have 2 copies of C2. So you have another endotrivial module, which has order 2 in TSN. And in fact, that's a Yang module. So we do know what this is. But that has a finite order. And one more case is when N is at least P squared and no more than P squared plus P, and then you get one more copy of Z. So in fact, it is the same for N in P. When N is at least P squared and no more than P squared plus P, you always have another module which is endotrivial and doesn't lies in the syzygy of N, the syzygy of F, and it generates a summand Z of TFSN. So I want to study this particular module which generates this summand, and what are the interesting things about this module. Okay, so I'm going to take the smallest one in these all cases, where is when P is 2 and N is 4. So I'm going to look at this endotrivial module for S4 in characteristic 2. Okay. So when P is 2, and consider the group algebra FS4. So first of all, S4 has order 4 factorial, which is 24. So the P2 part will be 8. So you will have those 2 subgroups of order 8. And in fact, the Celo 2 subgroup of S4 is isomorphic to D4, so it's dihedral. And we can pick, for example, the subgroup generated by permutation 1, 2, 3, 4, and the permutation 1, 3. And the P2 rank of S4 is 2. And the number of conjugacy classes of maxima elementary abelian 2 subgroups is 2. So you get 2 different conjugacy classes of maxima elementary abelian 2 subgroups. One is generated by the permutation 1, 2 and permutation 3, 4. And another one is generated by 1, 2, 3, 4 and 1, 3, 2, 4. So why do I want to point out that it has dihedral Celo 2? This is because a theorem by Auslander and Carlson says that if in characteristic 2 you have a Celo 2 subgroups of G are dihedral, then take the projective cover of F and the heart of PF, which is the radical quotient of the circle, will be a direct sum of a module M and the dual of M for some endotrivial module M. And this is where the other copy of Z comes in. So in fact, the TF, the torsion-free part of endotrivial modules for G, will just be generated by omega of F and this M coming from the heart of PF. So we know where to find this copy of this other endotrivial module of M. And in fact, this should be the case for S4 and S5 because the order of S5 is 5 factorial, but the P part, the 2 part is still 8. So the Celo 2 subgroup of S4 will be a Celo 2 subgroup of S5 as well. So S5 also has a dihedral Celo 2 subgroup. So S5 will also have this another endotrivial module M, which comes from the heart of PF. So in the case when we have S4, we are going to consider the Specht module for S4 is labeled by the partition 3(1), S31, and it has dimension 3. Okay. So I'm not sure if you are familiar with the Specht modules. So the Specht modules for the symmetric groups are an important family of modules. So they are defined for any Sn, and they are labeled by partition of n. In the characteristic 0 case, this Specht module, they gives you all the simple modules for Fsn. In the characteristic P case, when P is odd, these Specht modules are indecomposable, and in P odd case, they may be decomposable. But overall, in the characteristic P case, the Specht module will always have a simple head. And if you collect the head of this Specht module, you get a complete set of simple modules for Fsn. So, and we understand more about this Specht module. In general, they have a characteristic free basis, and they can be constructed in a combinatorial way, which the basis is just given by like the lambda polytabloids of the standard lambda polytabloids. Anyway, so what I want to say is that this Specht module arises naturally in the representations for the symmetric groups. And in this case, we are going to look at the Specht module S31, and we do have a basis for this S31, and it has dimension 3. And the S31, in fact, is a uniserial module. So it has F on the bottom and the D31 at the head, where D31 is a simple self-dual module of dimension 2. And I will use D to denote D31. So, in fact, FS4 only has one block. So it has a unique block and only two simple modules, which is F, the trivial module, and the D31. And we know the radical layers of the projective cover for F and projective cover for D. So the projective cover of F is over here, given, and you can see that the heart of this projective cover splits into two modules, DF and FD. In fact, since D is self-dual, so this FD is just the dual of this module DF. And this DF is exactly S31. So the heart of the projective cover PF is just isomorphic to S31 plus the dual of S31. Of course, we can say the same thing about the projective cover of D. It will split into two modules, D and Q. And in fact, this is actually a special biserial algebra, but I will not talk more about these things here. So I will name this module FF in the heart of FD as Q. So by the theorem of Auslander and Coulson, it tells us that this S31 is exactly the other endotrivial module we are looking for. And the portion TS4 is generated by the omega of F, the S31, and the sign sorry, actually we don't have the sign here because you don't have this sign in characteristic 2. So you will only have this 2. Okay. So now the question becomes, we have this module, we know the composition factor appears in this module. We even have a basis for this endotrivial module. So what can we see more about this module, right? Okay, so I want to study the symmetric power of this module. So first of all, why is that? FS4 has a 10 representation type. So it means that we have a way to sort of understand the indecomposable modules of this group algebra. And second of all, since S31 is endotrivial, and previously we said that if we take the nth power of endotrivial module, there will only be one non-projective indecomposable summand, and that summand is again endotrivial. So it means that even though it has time representation type, but in each nth power, you only have one thing coming out, which is not projective, and in fact, you can sort of describe them as well. And the nth symmetrical power is always a quotient of the nth tensor power. So it tells you there may be a way to understand the nth symmetrical power, since the nth tensor power is quite straightforward. You only have one thing that is not projective. And if I want to say more about it, so this S31, they had its union serial. It's 1D on the top and 1F in the on the bottom. And for this spatial biserial algebra, you can use words to describe the string modules appears. So in fact, all the non-projective indecomposable summands appears in this unsymmetric power of S31. There will be string modules again, and you can use words to describe them. You can even locate them in the Ostrander written components. So that's another reason I think we could try to understand more about the nth symmetric power. So we do have a description for the non-projective indecomposable summands appears in the nth tensor power as a word. So that's the goal, to study these things. Now, another reason is that there is a wonderful, beautiful theorem by these two authors. So they said that if you take the group algebra FG and any module A, the number of non-projective summands appear in all nth symmetric power of M will be finite up to isomorphism. So it tells us that if we want to describe the summands non-projective summands appears in nth symmetric power of M, it will be finite. So you do have a chance to success. Okay, but the proof of this one use a lot of homological algebra, and since they are dealing with more general types of modules, so they didn't actually talk about basis and everything. But for this Specht modules, we know it has a basis and it has dimension 3. So we were asking, can we describe what are exactly are the non-projective indecomposable summands appears? So that's my question. And the answer is yes. So before I state the last theorem, recall that we have this D, which is the head of S31, which is simple of dimension 2, and Q is the extension of FF, and let M be the natural module for FS4, and it is again uniserial given by FDF, and it has dimension 4. So in fact, we showed that all the indecomposable non-projective summands appears in the nth symmetrical power of S31 will just be given by the following modules: F, D, Q, S31, omega of D, omega of Q, and M. And furthermore, we can say what are the things appears in each symmetrical power. So they are given over here. So when n is a multiple of 4, you get one copy of F and some D, Q, M coming out. And when n is 4k plus 1, you get one copy of S31 and some omega D, omega Q, and M. And when n is 4k plus 2, you get D, Q, M with some coefficients. And when n is 4k plus 3, you get omega D, omega Q, and M. And I want to say that these coefficients, A, N, B, N, C, N, they are non-negative. So it could be 0 at the beginning, but eventually they will all be positive. Yeah. So this sort of gives us the main result. So we describe the summands appears in each nth symmetric power. Excuse me. So I want to give you an idea how we prove it. Okay, a quick one, obviously. So we are going to do this by constructing short exact sequence. So there is a short exact sequence from 2k symmetric power to 4k symmetric power to second exterior power of S times 2k minus 1 symmetric power of S. And there is also a surjection from second symmetric power of S times 4k symmetric power of S to 4k plus 2 symmetric power of S. And in fact, we show these two, the first short exact sequence split, and the second surjection also split. And also this second exterior power of S, it is the dual of S, is isomorphic to the dual of S. So this sort of give us information when this power is even. And for the odd case, it's more straightforward. When n is odd, we have that the nth symmetric power is isomorphic to the n minus 1 symmetric power tensor with S in the stable module category. So eventually, this will give us information when the power is odd. But you can see that over here we have some tensor products going on. So you have tensor with S, tensor with S dual, and tensor with second symmetric power over S. So we need the multiplication table of these non-projective summands appears. For the projective ones, since tensor with projective ones gives you projective, you can ignore. So you do want these informations to sum them up. So when n is even, when n is 4k, you have that the 4k symmetric power of S is just 2k symmetric power plus dual of S times 2k minus 1 symmetric power of S. And the 4k plus 2 symmetric power will be the direct summand of tensor product of these two. And the odd case is even straightforward, it will just be n minus 1 symmetric power times S. And the multiplication table, we can also compute them over here. I'll ignore the detail, but you know that we know most of the multiplication table. So how to construct the proof? So you do it inductively. So the first the zero symmetry power is by definition F. The first symmetry power is S itself. The second symmetry power, you do it by hand, it's D plus M. Now, when n is 3, you use the fact that when n is odd, it's just n minus 1 symmetry power times S. So you get D plus M times S, and D times S is actually omega D. So you get omega D plus M. When n is 4, the fourth symmetry power will be the second symmetry power plus S dual times first symmetry power. So you get D plus M plus S times dual of S. But S is endotrivial, so you get this is just F. So you get F plus D plus M. And when n is 5, you get back to the odd case, you directly take the fourth symmetry power and times S. So you get S plus omega D plus M. And when n is 6, it's a direct summand of the right-hand side, so you do the multiplication, and so on. So basically, this is how we did prove the main result. And furthermore, another reason I do care about this symmetric power of this Specht module is because if we take the spatial linear group SL32 and S4 it can be viewed as a subgroup of SL32. And the SL32, it has dimension 168 or something. Yeah, I think it's 21 times 8. So it will also have a CeLO2 subgroup of order 8. And in fact, a CeLO2 subgroup of S4 will be a CeLO2 subgroup of SL32. So SL32 also has a dihedral CeLO2. And take the natural module for FSL32 V. So it has dimension 3. And this V restricted to S4 gives us S31. So if you know the grain correspondence, the CeLO2 subgroup of S4 and the SL32 is actually self-normalizing in these two groups. So in fact, V and S31 are the grain correspondence of each other. So since SL32, it has a dihedral CeLO2, so the Auslander and Carlson theorem tells us that the part of the projective cover will split into two modules, V plus the dual of M, V, and these two modules are endotrivial. So the TF, the torsion-free part of SL32, will be generated by the seizure of F and V. And we know all this information for when in the case for S4. So we can ask the same. Can we say more about the symmetric power of V, the natural module? And we know that the symmetric power of the V, they sort of like, well, in the, I think in the characteristic P case, the number of composition factors are linked to some decomposition numbers. Anyway, but there are some motivation of studying the symmetric power of the natural module in the general linear group or the special linear group. So that's one of the reasons we look at the symmetric power as well. So we ask, what can we say about the symmetric power of V? So in fact, we have a similar analogous result for the symmetric power of V. So you will get all the indecomposable non-projective summands appears in nth symmetric power of V are just given by F, V, the second symmetric power of V, the omega of it, and R and omega of R. And over this R is a 11-dimension indecomposable module. And then we know explicitly what are the things appears in each nth symmetric power. So over here, when you have 4K and 4K plus 1, you will get a unique copy of V, a unique copy of F, or a unique copy of V. And in the case when you have 4K plus 2 and 4K plus 3, you have some coefficients AN and BN coming out. And in fact, if I want to say more, this V, as I mentioned just now, it is in grain correspondence with the module S31. And this second symmetric power of V is in grain correspondence with D. And this R is in grain correspondence with the module Q. And you can see over here, previously, in the previous result, we have this module M coming out all the time, right? But in the SL32 case, you don't have the module M. This is because this V and, this second symmetric power of V and R, when they restrict it to S4, they will have some module direct summand AM coming out. So the AM actually comes from when you restrict these modules to S4. So, and in that way, you can actually say more about the coefficients over here. Since this D corresponds to second symmetric power of V, this Q corresponds to R in the SL32 case. And this M comes from restricting these to S4. So the Cn will always be a sum of an plus bn in all these cases. And that's coming from the result over here. Okay. And last but not least, we actually have the same situation for S5. And we have an extra copy of Z coming out in TF-S5. And that extra copy of Z is generated by some endotrivial module N, where this N comes from taking induction of S31 to S5. And this N has a Specht filtration, so we know some information, and it will be endotrivial and generates one direct summand of TF-S5. So we want to do the same for this 11-dimension indecomposable module for S5 as well, and that is still ongoing. Okay, basically that's all. Thank you for listening.
Thank you. It's amazing. Do you have any questions?
I wanted to say that these results are very, very nice. I have a question. So do you have hopes to do a similar classification for P greater than 2?
Okay, so I think that's the next step. But when P is greater than 2, I think the problem is that the dimension of these modules, they will grow largely. That's one of the problem. So we can still try. And also, I think for this module, you have a very nice, the quivers for this FS4 and FS5. So you know what are the things appears in the projective covers, right? And when N is large and P is large, you have no control. You don't know the quiver. You don't know the Gabriel quiver. So things will get messy. You get wild representation type and everything. So I will say you will be much more complicated than.
Okay, yeah. And I have a very naive question beforehand. So you said, you gave all these results about how this group is, the form of the group for some P greater than 2 as well, right? You have a set 2 appearing that is associated with the sign representation, right? And this
yes.
So what would be the CCG of the sign representation? Would it be itself, or it should be F, or how it goes?
Yes, I think you will have. I think it will be itself. Yes. So you'll get a periodic module.
Yeah. Otherwise you would not have.
Yes. Yeah.
Right.
Yeah.
Okay. Right. But because you have this formula, right? That when you apply the CCG, and
yes,
it gives you. Yes. And so, no, this is only working for F, right? It doesn't work for the modules. Yeah. That was the confusion coming out. Right, because I was saying, well, if you change in that formula F by the sign representation, I was saying, well, 2 times should be the identity, and this is F. Yeah, but that doesn't work for the sign. Okay. Yeah, okay, thank you. Sorry.
Oh, no worry.
Any other question over there? I think I have something I was thinking, not a question, but and you already said something about that. What happens with induction? I don't get. You mentioned an induction then, but are there some things that happen generally with induction that you have, for example, induction and restriction and this endotriviality?
Okay. I think in general, you don't have good results because taking dual and taking induction, they don't sort of commute. You get what I mean?
Yes.
Yeah. But
yes.
taking restriction is fine. So if you have, I think there is a result saying if you have M is an endotrivial FG module, and you take restriction to some certain subgroup, you will get endotrivial module again. But you have some requirements on the subgroup containing the vertices or something.
Yeah, you mentioned that result at the start, I think.
Oh no, that's just elementary abelian P subgroup. So M is endotrivial if and only if M is restricted to any elementary abelian P subgroup is endotrivial. But ignoring the endotrivial P subgroup, for general subgroup, if I think the result could be containing the vertices or the normalizer of the vertices or something, then the M restricted to such subgroup will again be endotrivial.
So that induces like a group morphism between the T's of the groups.
Sorry, what's the question?
No, if that induces a morphism from the groups of endotrivials, or is there anything else to, I don't know, that can be spoiled by taking?
Yeah, but when you do restriction, they may not remain indecomposable again, right? So you may have a map, but it may not be isomorphism anymore.
No, isomorphism, no, of course, but okay. Oh,
does it behave well with the tensor product? In the restriction, that's.
Sorry.
I mean, is this map a map of? It's a group map, right? I mean, it's because the restriction behaves well with the tensor or not.
Yes, the restriction behaves well with tensor.
So you might have a non-zero kernel and co-kernel, but I mean you have a map.
From the group of
the bigger algebra to this group, yeah.
So you are saying you may have a group from you may have a homomorphism from TG to TQ for some Q.
Yeah, subgroup with by taking restrictions. That is not what how do you say?
Yeah.
Yes.
Yeah, I think that okay. Yeah, I think that makes sense. But I guess then you sort of have to study what's the kernel of this map and whether it's also you may get more indecomposable modules coming out for small subgroups, right?
Right.
Sorry.
Yeah.
Yeah. Or yeah. So you have a homomorphism which is not surjective and you have a non-trivial kernel in that case, I guess.
Yeah, you might get some conditions for
P
and Q for which the kernel is 0 or the co-kernel is 0 or
Thank you.
Not sure if I answered any of your question, but
yes. Yes. My question was if it was okay if it actually define a morphism, and just because you have all these groups described like explicitly and I don't know, imagining which copy goes where, and and that. Just because it looks nice. So yes.
So in particular, you could take this morphism. I mean, take the restriction from S5 to S4, right? I mean, you have this explicit description.
Yes, actually, the S4 and S5 they will have the same TTG because they have the same Silo2 subgroup, which is dihedra. So the TTS5 will be the same as TF. The torsion-free part of S4 is the same as the torsion-free part of S5. So it will be isomorphic to this square. So that's what it says here, right? In the last page.
Yeah.
So the torsion-free part of S5 is generated by omega of F and N. And this N comes from exactly the induction of S31. And in fact, if you do restriction of N to S31 to S4, then S31 will be a summand of this restriction. They are in current correspondence of each other.
I see.
But the thing is that when you take symmetric power, it doesn't behave well with induction.
Right.
It behave well. It behave well with restriction. Actually, like restriction is fine, right? But it doesn't behave well with induction.
Right.
So you cannot get more information from the fact that this is a direct summand of the induction. So you have to sort of work directly with this module N.
But for sorry, we are going down to this rabbit hole. But if you take restriction, so you're saying that the generators, and suppose that you know all the generators of your T groups, yeah. So if you take the restriction, the generators of TG would go to the generators of TQ for Q as subgroup, or not necessarily?
No, as I said, when you do restriction, you may have N is not indecomposable anymore, right?
Right. All right. Yeah.
Yeah. So it may not be the case.
Yeah. Okay. Yeah. Oh, very nice. Very nice.
Okay. Do we have more questions?
Not me.
Yeah.
Thank you.
That's
beautiful.
Yeah. Thank you, Jay.
Thank you.
So
actually, I'm a bit fuzzy. Like I don't know. Like where are you guys, Franco, and you guys? Where are you guys right now? Are you guys in a university or something?
Yeah. In Buenos Aires. Yeah.
In Buenos Aires.
Yeah.
Yeah, in Buenos Aires. Yeah. Where we gather in a meeting room to watch the